Hi, I'm Skyler.
I'm Nathan.
So for our project, we decided to do gradient descent on patient data, patients who have had heart attacks and recently been admitted to the hospital.
Our data set contains 111 features and uh, 12 target variables, and the targets are complications that arise for these patients. So we decided to focus on uh, features that are available at the time of admission to the hospital. So we had to remove some columns.
Yeah. So that kind of brings us to the whole data processing. So first, um, thankfully, this data set is available as in a Python package, so it's very easy to load and fetch. So this is the whole myocardial data set. And then we specifically took those columns, um, so like 93, 94, all of those we can just exclude. Um, and then also for data processing for gradient descent, we want to determine which columns were numerical and which were categorical. So we had to comb through all of these and find like all of the numerical, categorical. It's kind of painful, but we got through it. And so those are all of these. And then basically we cleaned these so that there are no numerical or categorical in the excluded columns. Um, and then proceeding from there, we ended up changing from indices to column names partway through because it is a pain. Um, and then we also decided to clean the data for any columns that have any more than 20% of missing values. We kind of chose that arbitrarily, but we found there's a kind of grouping of columns that had that. So then this code here sort of goes into that and then drops those columns. And then for all the columns that had missing values less than 20%, we used an imputer to using a mean to basically fill in those values. Um, and then we performed one hot encoding on the categorical columns. And then after that, what did we do? Um, so yeah, we removed those original columns and then added the one hots back in. And then finally, we ended up scaling all the data so it's on a scale from 0 to 1.
That was particularly important with age, so I
Yeah.
wouldn't have ages that are like going from like whatever 20 to 99.
Yeah. um, so yeah, this was our resulting full data set, which yeah, fun stuff. Um,
So we decided to do an 80-20 train test split, and that gave us uh, for the training data set it was 1,360 or 60 rows, and for the test data set it was 340 rows.
mhm. And also importantly, we had 148 features after all of this, after like the one hot encoding and all that stuff, and 11 target variables. Um,
So these are the functions that we made. Well, kind of took from one of the exercises,
yeah.
partly, to implement gradient descent.
Wait, one sec. Sorry, I don't
Oh,
think I ran this one.
oh.
Um,
So yeah, we have like the average gradient function, gradient descent function, and then these functions for the accuracy calculations. And then down here is our function for noisy gradient descent, which satisfies epsilon delta differential privacy. Uh, we have an argument here, so it's a counting query, so sensitivity is 1 for the Laplace mechanism. And with the Gaussian mechanism, we clip to have an L2 norm of at most 3. So the sensitivity of that sum is 3. And then for the composition, it we split the epsilon, or divide epsilon by iterations plus 1 for each time we use it. And it's used once for the Laplace mechanism and then once for every iteration. So that in total is epsilon. And we split up delta by dividing delta by the number of iterations. And we use that once for every iteration. So that's a total delta of delta.
yeah.
And then post processing, everything each update's based on differential values for the theta. So the final model satisfies differential privacy by post-processing as well. So we tried that, and that's kind of where we started run into some problems, because in the training data, most of the target values are 0, so meaning that complication wasn't present for that patient.
Yeah.
And when we tried to use gradient descent, it just decided that there were no complications ever. So we had to use oversampling to kind of combat this and almost force the model to start predicting some complications being present. So we decided to use mode oversampling, and this was us just trying it out. And as you can see, it now predicts an equal amount, or not predicts, now it's an equal amount of ones and negative ones in the training data. So
this is just doing a run through using it.
Oh yeah. Yep. So we ran through and tried gradient descent with the SMOTE oversampling, and it came up with a final accuracy of, well, for this column, which was Dressler syndrome, of 99.7, which we were pretty happy with. Yeah. And as you can see from the cell below that, it did actually predict both ones and negative ones.
Which is what we want.
Yes.
And so then going on from there, clearly, as we've kind of alluded to earlier, we have 11 different target columns. So the kind of regular gradient descent isn't really made for or tailored specifically for like choosing a specific column. So we kind of made a couple functions that would work for individual columns. And then after this, we did a little bit of testing with the noisy gradient descent and everything, and the regular gradient descent, and we found that with our regular gradient descent, we get a lot of overstepping the minima of the gradient itself. So essentially on like even iterations, it would get to the bottom of the gradient. We had really good predictions. And then on odd iterations, it would basically step out of that minima, and we get really bad predictions.
So it would go from being like 98% accurate to maybe like at most 50%.
Yeah. So then we did a little bit of research into it and how to sort of correct this. And we decided we didn't really get it from any sort of research, but we decided that, if we're going to decrease the step size, we can basically multiply it by something that's like decreases the step each time. And so this quote unquote learning rate is basically just some value between 0 and 1 that'll basically just decrease how far it moves at each step in the gradient, so that it kind of corrects for that overstepping. You'll still have a little bit of overstepping, but it won't be as severe as going from 90% to 40% on consecutive iterations. And so these functions all are kind of implementing that, and additionally working with specific columns too. And then so we did both gradient descent and noisy gradient descent with this. And yeah, so this ended up working very well. We found that with just general gradient descent on its own, if you have a very high number of iterations and a very low step size or learning rate, you can get very high predictions. In our write-up, we just gave an example of all of the different accuracies for both gradient descent and noisy gradient descent for a 10 iterations and 0.5 learning rate, I think this was. And the gradient descent got to 1, which is pretty impressive. Actually, I think this might be 100.1. No, it isn't. Never mind. My bad. But yeah, so it ended up working. It ended up helping it a whole bunch. I think that's it.
And this last cell is just for, it's for making those tables, right?
Yeah. And basically, it just goes through all the different target columns and runs noisy gradient descent 100 times and then averages those. It also runs the just regular gradient descent just once. You don't need to run a gradient descent 100 times because it's just going to be the same every time. So yeah, and then so this takes a while to run because it's a lot of iterations, especially when I was testing it, because we have various learning rate and we have various learning rate and iteration combinations. So 0.1 learning rate and 100 iterations, that took like an hour and a half to do. So don't expect this to run fast. But yeah, I think that's about it.
That's our project.